Principles and Practice. I'm Craig Simmons, Director of the National Centre for Groundwater Research and Training in Australia, and it's my pleasure to introduce and chair this webinar. Thanks for joining us for this fourth webinar today, which is part 2, overview of data assimilation technology, uncertainty analysis and optimization. Today we'll be joined by John Doherty, and we'll hear from Jeremy White via recorded video. If you've been attending the series, you'll have noted the webinars have generated a lot of discussion, which is absolutely fantastic. And as a result of this interest, we'll be hosting a 5th webinar on the 17th of June to discuss and reflect on how to apply decision support modelling concepts in everyday practice. And it's really designed to be a worldwide global conversation about groundwater modelling. And we really encourage you to register for this webinar. We think it's going to be a really interesting and exciting event. An email will be sent to you containing registration information and where to send any questions or discussion items you would like presented following this webinar. A reminder that all video recordings of the webinars can be found on the GMDSI video channel. Meanwhile, during today's webinar, we encourage you to send your questions to us in the Q&A box, and we'll answer those that we can in the time that we have at the end of the presentation. And you can use the chat box for any comments or discussion. I'd like to again thank John, Kath, Jeremy, and the whole GMDSI team for this interesting and important webinar series. And we couldn't do any of it without the tremendous help from Fiona Adamson in the NCGRT, who is hosting this webinar today and is our backup support. So without further ado, I'll hand over to John Doherty to get things going. Over to you, John.
Thank you, Craig. So with that, I share my screen and I turn my video off. So hello everyone, and thanks for joining us. As Craig just said, you'll be hearing from me for a little while, and then you'll hear a video from Jeremy White. So this is our topic for today, options for nonlinear uncertainty analysis. And this is the 4th in a series of 4 webinars where we started with the concepts, moved through, developed those concepts, moved through the repercussions, and are now finishing off with the tools. So this is our agenda for today, and I'll hand over to Jeremy for this part on ensemble methods. So, as always, we start off with a little bit of revision. And as always, we start off with Bayes' equation, our guiding light. Bayes' equation talks about the need for data assimilation. It talks about the need to make predictions associated with environmental management and to quantify the uncertainties of those predictions. And remember back in webinar 1 we said, well, Bayes' equation tells us what to do, but there's other branches of mathematics which can shine a little bit of light on how to do it. We said it's all about the passage of information, and linear analysis, which we talked about last time, can actually show us the flow of information from information that's resident in data of 2 very different types, the historical behaviour of the system and the expert knowledge, each in different terms of Bayes' equation, as we'll talk about shortly. We said that taking that concept of flow of information, we can define 3 categories of predictions. Those here on the left, where predictions are pretty much totally informed by the historical behaviour of the system. In the middle, sometimes we have to make predictions for which the historical behaviour of the system sheds very little light on what the prediction's going to be. And then there's a 3rd type, which we've called blended, where the prediction is partly informed by the historical behaviour of the system and partly informed by expert knowledge and the stochastic nature thereof. And we said that depending on what type of prediction we've been asked to make through the modelling process, we may design the modelling process very differently and assimilate data or not very differently. We said last week that to think of a model on its own, to think of a simulator on its own, if we're going to take the decision support imperative seriously, doesn't really make sense. If it's all about assimilation of information, if it's all about working in a highly parameterized world, and this type of prediction here, this mixed prediction, this is the area we're living in today, where we're assimilating data of very different types from very different sources pertaining to very different scales. For reasons we talked about in the last 3 webinars, we have to live in a highly parameterized world to quantify uncertainties and to preclude bias being introduced to predictions through history matching. And if we are going to assimilate information, if we are going to quantify uncertainty, the model on its own makes no sense. Modeling really becomes a verb and not a noun. And the modeling process done in the decision support context has to be done in conjunction with what I called modeling dancing partners, software packages of equal complexity that can run a model many, many times in order to perform the data assimilation and uncertainty quantification tasks required by decision support modeling. 2 fundamental specifications for modeling dancing partners are: 1, a non-intrusive interface with the model. That is, it can interact with the model through the model's own input files and output files. And secondly, the ability to parallelize model runs. Last time too, we spoke briefly about model calibration, as Catherine did back in webinar 1. We said that calibration, we need to define what it means. It's not history matching. History matching is more general. We're history matching today, but we're not calibrating. Calibration has that sense of uniqueness associated with it. Uniqueness where uniqueness has no right to exist. Uniqueness that we manufacture by imposing certain conditions on the parameter field that we derive through history matching. And those conditions are that we have an ability to make predictions whose potential for wrongness is minimized. Now, that doesn't mean that potential for wrongness can't be high. It's just that that potential is symmetrical with respect to our predictions. If we do everything right when we calibrate, seeking uniqueness in this very special way, we're able to populate a model parameters with the heterogeneity that must exist to explain the historical behavior of the system. Today, our task is to populate a model with many different realizations of parameter fields which may exist that are compatible with the historical behavior of the system. We wander into parameter fairyland today, but in a way that maintains the fact that we can still history match well the historical behavior of the system. And then last time we also spoke about linear analysis, which we can use to quantify the uncertainties of parameters and of predictions, but only in an approximate sense. We also saw how linear analysis could provide some pretty powerful insights into flow of information, the worth of data, the contribution that different types of parameters and boundary conditions and other facets of model construction make to the uncertainties and or errors of critical predictions. So linear analysis is good for insights, but a little bit approximate. Today we move away from approximation and we do full nonlinear parameter and predictive uncertainty analysis. So let's define the problem. We start off as usual with Bayes' equation, and let's start off by examining the terms of Bayes' equation in just a little more detail than we have done in the past. So firstly, the prior parameter probability distribution. Now, I've just drawn a one-dimensional prior parameter probability density function here, but let's keep in mind how simple this picture is. We could be working in parameter spaces with 10,000 dimensions, so these pictures are very simplistic. Nevertheless, I hope they are illustrative of the tasks that nonlinear parameter and predictive uncertainty quantification places before us. So now, suppose I take a sample of that prior parameter probability density function. What do I mean? I generate a parameter field randomly, a realization of parameters from that prior parameter PDF. Then I run the model. And after running the model, I ask myself, does this fit the field data, the historical measurements of system state well enough? Well, I can't answer that question until I define well enough. And this is where this second probability distribution comes in. Now, we assume that when we make measurements of system state in the field, that those measurements have noise associated with them, measurement noise. Now, we know that measurement noise isn't the only reason that we can't fit field data with a model. We know there's model noise, or structural noise as it's sometimes called, but just because it's too horrible to do otherwise, we normally class it as measurement noise. And in so doing, we give it a probability distribution, the probability distribution of measurement noise, or whatever it is that's responsible for model to measurement misfit. Once we have a probability distribution, we've got a metric for model to measurement misfit. So what I'm saying here then is that I've just tried to fit the field data. These little differences between field data and model outputs are called residuals. Now, these residuals, do they have a finite probability according to this so-called likelihood function, which is in fact a probability density function, the probability density function of measurement noise? If it does have a finite probability, then bingo, I have sampled the posterior parameter probability density function. Bayes' equation, say I multiply this probability by that probability to get this. Qualitatively, if I've sampled the prior in such a way that model to measurement misfit satisfies the likelihood function, I have sampled the posterior parameter probability density function. Now this is important. In general, we cannot come up with an equation for this posterior probability density function. We may have an equation for the prior. We may have an equation that describes the likelihood function. But because our model is nonlinear, we will not have the luxury of being able to provide or associate an equation with the posterior parameter probability density function. We can only learn about it by sampling it. That's our job, to come up with as many, well, with a lot of realizations of the posterior parameter probability distribution, and thereby define it through having sampled it enough. And all the while living in high dimensional parameter spaces. So our mission, should we choose to accept it, goes like this. We sample the prior. We sample the prior by generating parameter fields which are realistic according to my concept of realistic based on my prior probability distribution. Now, as we've said in the past, there's a whole field of study called geostatistics, whose task it is to give voice to the prior probability density function of parameters. That is, to give voice to figments of geological imagination. They can be considered to be samples of the prior probability density function. Normally, however, when we do this, we normally use parameter fields which are not quite as, well, let me use the word realistic, but only loosely, as these. Not quite as realistic as what might come out of modern day geostatistical simulators. Parameter fields which can express heterogeneity but which are somewhat abstract in nature because we need to adjust these for reasons we'll talk about shortly. So we sample the prior. We come up with a realization of a set of parameters throughout our model domain, and that set of parameters is in accordance with the prior, and it may be somewhat abstract in nature, so it can be adjusted. Now, but we've got to do this in a special way. We have to sample the prior in such a way that when we run the model, we get a good model to measurement fit, with the metric being the likelihood function. And by doing that, we've sampled the posterior. And if we do that often enough, if somehow or other we can generate realizations of the prior parameter probability density function, which all give us a good model to measurement fit as judged by the likelihood function, then we're sampling the posterior, and by sampling the posterior, we are defining the posterior. And then when we have done that enough, when we have attained enough samples of the posterior parameter probability density function, we then run the model into the future and we sample the posterior predictive probability density function. Now that all sounds easy, and it sounds conceptually easy at least, but let's not forget one thing. I can draw these nice little schematic pictures here in one-dimensional parameter space. Consider this all in 1,000 or 10,000 or 1,000,000 dimension parameter space. It is not easy to sample that little corner of parameter space, that little 10,000 dimensional hypercube of parameter space that's going to give us a good fit with the field data. Therein lies the challenge, should we choose, and that's our mission, to accept that challenge. And that's what we're doing today. So, let's have a look at how can we do this efficiently then in high dimensions. Well, there's three basic strategies, and the methods we're going to talk about adopt them all to a greater or lesser extent. One is, well, kind of preempting the answer. We can confine our sampling to this region of parameter space, wherein the parameters do satisfy the likelihood function, the posterior parameter probability distribution. If we've got some clues as to where this is, we can confine our sampling to this area, and that can make our task easier. Second strategy is to sample all of parameters, all the prior probability distribution, and then adjust the parameters that we come up with, the parameter fields that we sample, until the model outputs match the field data. And the third is a combination of these. We're going to be talking about methods which adopt all of these strategies, but bear in mind the difficulties, all the while, the difficulties of working in parameter spaces which are of very high dimension, as they have to be for reasons we've talked about a lot. We have to live in this highly parameterized world to quantify the uncertainties of decision-critical predictions and to make sure that we don't incur bias in those predictions through having too few parameters. Okay, so let's look at some of the ways we can do this. The first is a very inefficient way, but it still has some good things about it. One of the good things is that we can actually use these beautiful parameter fields that may arise out of modern day geostatistics. We can use very complex random number generators embodied in geostatistical software to generate figments of imagination conditioned by borehole data that we may have that can be considered samples of the prior parameter probability density function. So we generate these, we sample the prior probability density function. We run the model. Surprise, surprise, not many of those, if any, allow the model outputs to fit the field data. So here's our likelihood function, and I'm assuming here that 2 of those parameter fields give us a model to measurement misfit, which is passable according to the metric of the likelihood function. Then I throw away those that don't satisfy that metric. What's left is a sample of the posterior parameter probability density function. This, for obvious reasons, is called rejection sampling, and it has some good things and some bad things. The good things are it's easy conceptually, it couldn't be easier. Provided certain conditions are met, it is strictly obeys Bayes' equation. It does allow us to use these types of parameter fields, and remember back in webinar 1 we said that if we're making those kinds of predictions for which the past is not very informative of the future, there really is no need to fit the past. And by putting all our states into geostatistical software, by putting our knowledge into geostatistical simulators, we can express our expert knowledge using best available technology, not worry too much about fitting the past, only reject those samples that give a particularly poor misfit. So they're the good things about rejection sampling. The bad thing is, in a high-dimensional parameter space, the hit-to-miss ratio is going to be abysmal. If we want even a halfway good fit with the data, we're not going to get it unless we do an unseemly number of model runs, more model runs than we probably have the numerical capacity to bear. So this isn't often used. So now let's look at some more efficient methods. And the first one we'll look at is pseudo-linear methods. And historically, these have go under that broad category of methods that have been referred to as null space Monte Carlo in pest parlance. So, remember from the last webinar, we said that suppose we've calibrated a model, we've history matched the past, so there's the past on top, and there's the future below. And with our model, we history match the past, and then we make a prediction of the future. And if we calibrated, that is, we sought uniqueness in ways we've talked about, and if we did that using a Jacobian matrix calculated using finite differences, this Jacobian matrix, it has integrity, enough integrity to be used in combination with other matrices we talked about last week to calculate a linear approximation to the posterior uncertainty of parameters. That is, this posterior parameter covariance matrix can be calculated relatively easy once we've got this Jacobian matrix. And these other matrices, this one here, which is the prior covariance matrix of parameters, easily calculated, covariance matrix of measurement noise, these are the two terms on the right of Bayes' equation. We can calculate a linear approximation to the posterior uncertainty of our parameters, and thence, by running the model into the future, of predictions. Now, what we can do is we can sample this approximation to the posterior parameter probability distribution. Now, because the model isn't linear, and that is only an approximation. However, often it's not a bad approximation, and it puts us well and truly in the ballpark of that part of parameter space that we need to be approximately sampling the prior probability density function. And if we've calibrated and if we've got a good Jacobian matrix, this is relatively easy to do. So here we are, coming back to our schematic. We've just found this sample from the prior parameter probability density function. We've got a good fit with the field data. We've got parameters of minimum error variance. We sample our linear approximation to the posterior parameter probability density function. We're still in the right region of parameter space. We may throw some of these away, but using the same Jacobian matrix that we used to calculate the linear approximation to the posterior parameter probability density function, we can adjust all of these parameter fields here that don't quite fit the data with the maybe 3 or 4 or 5 runs per parameter field. We can pull them back into calibration, and we're sampling the posterior parameter probability density function. Here's an example. This was a model that I had a bit to do with a few years ago in conjunction with colleagues of mine from the St. John's Water Management District, St. John's River Water Management District. Here's the calibrated parameter field in layer 3 of this particular groundwater model. Here are a few of the 500 realizations we then generated, all of which satisfied geological expert knowledge, all of which allowed us to fit the field data, that is the heads, and I forget how many wells, but there was an awful lot of them, all through the model domain. Then when we make a prediction, in this case, the flow in a spring after increasing water extraction in the vicinity of that spring, we can associate an uncertainty with that predicted spring flow. So in this left-hand side, I've got the cumulative probability density function of spring flow. We can see the uncertainty here for this particular case, for this particular spring, is 20 cubic feet a second. But here's something interesting. Once we have all these parameter fields in our pocket and we can run them into the future and look at the uncertainty of any prediction, we can also look at the uncertainty of predictive differences. So in this case, I'm looking at the uncertainty of the difference between spring flow under historical conditions and spring flow with the increased pumping. And notice how the uncertainty of the diminution of spring flow is much less than the uncertainty of the prediction of spring flow. And I find this nearly every time I do this kind of analysis. As we said a couple of webinars ago, models are much better at predicting differences than absolutes, and this may say something about how we should use them in decision support modeling. 2 webinars ago, we said something about how we should use them in history matching, following from this same concept, that models are better at predicting differences than absolutes. Okay, pseudo-linear methods. The good things are, once we've calibrated, they're easy to do and we get really good fits with the data, just as good as we got when we did the calibration. The bad thing is that, well, we have to calibrate first, and we have to have a Jacobian matrix which has integrity. If we've got a lot of parameters and we're calibrating using a high integrity Jacobian matrix, that's going to take a lot of model runs. That is the cost of this method of doing posterior uncertainty analysis. That is the cost of calibrating first and generating a Jacobian matrix with integrity. And as we'll mention now, and Jeremy will talk about in detail, that cost is avoided when we use ensemble methods. So before Jeremy talks about it, I'm just going to say a few words about an ensemble smoother, just to use the same pictures that we've used up until now, so that you have an ability to compare this method with the other methods and with a method we'll talk about after Jeremy's video is complete. So with an ensemble smoother, we generate realizations of the prior probability density function. Realizations of parameter fields, samples, of the prior probability density function. These have to be adjustable, so they're a little bit abstract. We'll talk a bit more about that later. Okay, so the thing here, as Jeremy will explain, is rarely do I have to generate more than 500 of these. I only have to have as many as the dimensionality of my solution space, which will rarely exceed 500. So that cost of 10,000 model runs to calculate a high integrity Jacobian matrix has gone. I don't have to calibrate first. I can, but I don't have to. So I generate parameter fields, run the model. Not many of them fit the data. But then based on a covariance between each parameter and each model output, with a little bit of matrix wizardry, I can generate an approximate ranked efficient Jacobian matrix. Now, in some ways, this matrix is rubbish. You can't do linear uncertainty analysis with this matrix, but you can adjust parameter fields to get a better fit with field data. So, using that matrix and using the same formula that I showed you last week, same formula PEST uses, this one matrix, we can adjust all these parameter fields until we get a better fit with the measurements of system state. We run the model 500 times again, look at the fit we get, but now we've got the ability to build another ranked efficient Jacobian matrix, which allows us to adjust those parameter fields to get a better fit. You do that for a few iterations. We've gone from sampling the prior to sampling the posterior, perhaps with only a few thousand, if that, model runs. So stunning gains in model run efficiency. There's good things and bad things. The good thing, obviously, is the huge leap in efficiency that we've gained. There are contexts, as Jim will explain. If your model's big and awkward and delicate, things can break down. Under some circumstances, you mightn't get as good as fit with the data as you can with traditional methods. But in a lot of cases, as we've talked about, getting a good fit isn't everything. So that may or may not be a problem. These are indeed a breakthrough, and they certainly add a very powerful tool to the assemblage of tools that we have for undertaking nonlinear posterior parameter uncertainty analysis. Now, with that, I'm going to hand over to Fiona to play Jeremy's video, and then I'll come back.
Hello, and welcome to my video where I will present a brief introduction to ensemble methods in the context of environmental modeling for decision support. In this video, I'm going to briefly cover the theory and practice of ensemble methods in the context of environmental modeling. Then I'm going to present a worked example where we applied ensemble methods to a numerical groundwater model to support risk-based decision making. And then finally, we're going to step back and examine the value that prior Monte Carlo brings to environmental modeling analyses. So with ensemble methods, the fundamental concept is we want to approximate model-based relationships using ensembles. There's typically two ensembles. One is a collection of randomly sampled model inputs. We call this the parameter ensemble, and there's a corresponding collection of model outputs. Typically, the parameter ensemble is drawn from the prior parameter covariance matrix in initial parameter values. Then each of the realized model inputs that we have drawn are run through the model to fill in the corresponding observation ensemble. Many of you will recognize this as a Monte Carlo analysis, and in fact, ensemble methods combine Monte Carlo and linear algebra to great effect. So what types of relationships might we want to approximate with ensembles? In the state estimation world, we want to approximate measured and unmeasured model outputs through covariance estimation using ensembles. In the parameter estimation setting, we're interested in approximating cross-covariance or gradients between model inputs and outputs. And what's fundamentally great about ensemble methods, especially in the parameter estimation setting, is they combine uncertainty analysis and history matching into a single algorithmic workflow. Now, there are three basic types of ensemble methods for data assimilation: batch estimation, sequential estimation, and then a combination of batch and sequential estimation. And we'll cover these three now. Batch estimation, typically referred to as ensemble smoother, treats the entire historic period as a single batch, where we simultaneously attempt to assimilate all historic observations. Now, this workflow is very similar to what we call history matching or calibration, and batch estimation is more computationally efficient than its counterparts. But because we've been treated the entire historic period as one batch, we lose some of the possible insights we may gain around model error compared to the filter. And because we're treating the entire historic period at once, This algorithm may be suboptimal for temporally evolving processes like saltwater intrusion, subsidence, and contaminant transport. On the other end of the spectrum is sequential estimation. This is where the ensemble Kalman filter is from, and this algorithm is used extensively in operational modeling and one-step ahead forecasting. But in the parameter estimation setting that we're interested in, to apply sequential estimation, we want to discretize the historic period into a number of cycles and assimilate observations in each cycle independently. So in the mod flow world, we would treat each stress period as if it was the only stress period and assimilate observations that occur during that stress period and then move forward to the next. But to do this, we not only need to track observations, we also need to track all simulated states, because the simulated states from the previous stress period become the initial conditions for the current stress period. And this means we need to be able to hot restart the model, and this brings with it some additional computational overhead and more bookkeeping. But because we're repeatedly applying the parameter estimation problem throughout the historic period, and implicitly we're getting forecasts of what the next stress period may look like, and then we see the observations of what actually occurred, we can actually close the predictive loop several times and start to build up a statistical picture of how the model is deficient. This means the ensemble Kalman filter may offer some statistical advantages in terms of accounting for and possibly correcting for model error. And in the same way, the Kalman filter may also offer some advantages for temporally evolving processes like saltwater intrusion, subsidence, and contaminant migration. Now the third algorithm is the combination of the two, and it's referred to as the ensemble Kalman smoother. And in the Kalman smoother, for each stress period, if we continue with our mod flow example, for each stress period we run the model from the beginning to the current stress period and assimilate all observations that have occurred. This is in contrast to the filter where we run one stress period at a time. And so because of this, it's more computationally demanding, but the ensemble Kalman smoother may be optimal in terms of its ability to close the predictive loop and account for model error phenomena. Now let's talk about how we approximate linear relations and gradients using ensembles. I will focus entirely on the parameter estimation setting and specifically on the Jacobian matrix. The Jacobian matrix is a first-order sensitivity matrix that represents the relationship between inputs and outputs of the model. Here we're looking at a single entry in the Jacobian at parameter j, observation I. And at that location, we would find a value of minus 0.2. How do we get this value? Typically, we would use finite difference approximations so we can be model independent. And what that means is we would run the model once at the initial parameter value of 3, which yields an observation value of 2.5. Then we would perturb our parameter value to 5 in this case, run the model again, get a different observation value, and our slope, our gradient, is just the change in the observation over the change in the parameter. Now let's look at how we would approximate this same gradient with an ensemble. In this case, we would generate many random parameter values, in this case 100, run each of those 100 parameter values through the model to get the corresponding 100 observation values. Taking those two vectors, we can calculate a correlation coefficient, scale that correlation coefficient by the standard deviation of the observation and the parameter, and now we have an empirical gradient estimate. In this case, minus 0.14. Slightly different, but telling the same story. I'm sure many of you are now wondering, why would we want to use an ensemble approximation that took 100 runs to get a poor estimation of the gradient compared to the 2 runs it took to get a finite difference approximation? In this case, you're correct. But if we think to the case where we have 1,000,000 parameters, that would take 1,000,001 model runs to fill in the Jacobian matrix using finite differences. But using ensemble approximations, we can use the same 100 model runs across all 1,000,000 parameters to estimate gradients. And that little trick is what allows ensemble methods to scale so well. Now, beyond the classical data assimilation algorithms using ensembles, there's the iterative form of each. And in this case, we're going to talk about the iterative ensemble smoother. The reason the iterative ensemble smoother must iterate is the same reason that PEST must iterate. And that's because even though we're using a Jacobian matrix to represent the action of the model in a first order sense, the relationship between parameters and observations is in fact nonlinear. So the basic workflow here is we use the ensemble to approximate the Jacobian matrix, and then using that approximate Jacobian matrix, we use the Gauss-Levenberg-Marquardt equation to upgrade the parameter ensemble. Now, if we start with our initial parameter ensemble P here, typically drawn from the prior parameter distribution, in this case, P has 3 parameters, HK, recharge, and starting concentration, and 4 realizations. Each row of the P matrix represents a set of parameters that's needed to run the model. And so the first step in applying the iterative ensemble smoother is to run the prior parameter ensemble. And we run that through the model. It can be done in parallel, and we fill in the corresponding rows of the DSIM matrix. The DSIM matrix in this case stands for data simulated. And in this case, we have 3 observations: head, concentration, and flux. After we filled in the DSIM matrix by running the model, we subtract the mean values off of both the parameter ensemble and the DSIM ensemble. And using those so-called deviation matrices, we can now form an approximate Jacobian matrix using this little bit of linear algebra. But this little bit of linear algebra is extremely important because it allows us to make the link between Monte Carlo and gradient-based methods that are highly efficient for parameter estimation. Using that approximate Jacobian matrix, we plug that into the ensemble form of the regularized GLM equation, and that yields a parameter upgrade matrix, P delta. P delta has the same shape as P, and in fact we add P delta to P element by element, thus yielding a new parameter ensemble, and that completes one iteration of the ensemble smoother algorithm. Now, as we continue, we now run the new parameter ensemble through the model again, completing a Monte Carlo. We form a new approximate Jacobian matrix, and around we go. Now, 2 important points here. One is, no matter how many parameters we're using, if it's 1 or if it's 1,000,000, the number of forward model runs required is controlled by the number of realizations. So now we've broken that relationship that's required for finite differences by using ensembles. And the second point is, since P starts as a draw from the prior parameter distribution, and we upgrade it in meaningful ways so that it better reproduces historic observations, that means when we finish, the P matrix, the parameter ensemble itself, is a sample of the posterior parameter distribution, which we can use for uncertainty analysis. That algorithm has been coded up into PEST-PP-IES, and like the other members of the PEST++ suite, it's fully compatible with PEST because it relies on the same file formats, and it also relies on internal default values for specific algorithmic controls needed to operate the iterative ensemble smoother. Users can override these by adding additional options to the PEST control file. There's a couple of other ensemble tools under development currently that I want to acknowledge. One of those is a data assimilation tool that implements the classical Kalman filter, Kalman smoother, and smoother, and that's being headed up by Ayman Alziri, and also a sequential quadratic programming tool that uses ensembles to approximate the relationship between decision variables and objectives for nonlinear constrained optimization, and that's being headed up by Matt Noling. I'm very excited about both these tools. Look for them to be released in the near future. Now, the pros and cons of using ensemble methods compared to the standard workflow we're used to, the vector form of GLM that's in PEST and PEST-HP. Now, the cons are, because we're using an ensemble, practitioners must be more deliberate in the way they construct their workflows, and that's because the cost of getting a new output is now much higher compared to running the model once. Now we have to run that entire ensemble. There's a problem called spurious correlation, which we'll talk about in a moment, and also model instability that may be brought forward by using randomized parameter values to run the model. But if you can see past those negatives, there's some pretty big positives. One of those, the most obvious one of those, is the computational efficiency you get from ensemble methods. You also get uncertainty for free, just as a byproduct of using the methods, and because we require less precision in the gradient estimation process, we can relax some of the forward run solver tolerances to gain back some of that computational efficiency. So what are the workflow implications of using ensemble methods? Well, in the standard workflow, we seek a single minimum error variance parameter set, and we then use that parameter set to run the model forward for predictive scenarios, and also if we need to just check something, we run the model once. But now in the ensemble world, each of these operations requires hundreds of runs, right? We no longer have a single best fit model. We now have hundreds of models, hundreds of parameter sets. which means running scenarios now requires many more runs, and just checking something new requires many more runs. And that because of that, the cognitive load on practitioners can be higher, but the PEST interface affords a perfect way to deal with ensembles, because you can construct your PEST interface in model independent ways, so you can set up observations for anything from the model you might ever be interested in, and then you can use the parallel run management capabilities of PEST and PEST++ to evaluate your scenarios in parallel. Now let's talk about this issue of spurious correlation and how it's addressed with something called localization. So this is our plot from earlier, where we have our high precision finite difference gradient and our less precise ensemble-based gradient. In this case, they're not so bad. The ensemble-based gradient tells the same story. But using far fewer samples, we can actually generate what is known as a spurious correlation. If in fact the finite difference gradient between this parameter and this observation was 0, so that there's no relationship, simply by using very few realizations, which is going to be the standard operating procedure in this case, we can generate a correlation that's erroneous or spurious. Why this matters is because with these spurious correlations, we can overcondition our parameters, right? That can lead to an underestimation of posterior parameter uncertainty, which in and of itself isn't a bad thing, but that posterior parameter uncertainty underestimation will lead to underestimation of forecast uncertainty. And that's a problem. And it's a problem for the reasons that John and Kath have talked about. If the possibility of a bad thing does exist, but the modeling results don't properly represent that probability, that's a failure. And for those of you who are interested, here's a graphical depiction of failure with modeling. So how do we overcome this problem? This is typically addressed through something called localization. And localization, in effect, allows us to inject expert knowledge into the ensemble-based algorithm to eliminate or remove non-physical correlations. Mechanically, this is done by building up a matrix, and this matrix lists parameters and observations and has values between 0 and 1. A value of 1 says, I want to continue with the ensemble-based correlation coefficient, and a value of 0 effectively removes that correlation coefficient. There's also something supported in the PEST++ suite called automatic adaptive localization, which seeks to identify statistically significant correlations and build up this localization matrix for you on the fly. Now, the last problem we deal with in the ensemble world is model instability. This is a mechanical problem, and it arises from using purely random parameter values, which can cause the forward model run to crash, right? But in the ensemble setting, each individual realization has a pretty low value. It's the collective value of the entire ensemble that we need for estimating those correlation coefficients. And because of that, we can use some greedy run manager settings to give up on runs that are taking a really long time, and we can also tolerate model run failures. Now I'm going to present a worked example of using ensemble methods at scale in a real-world setting to support resource management decision making. This example is from the Edwards Aquifer in Texas. The Edwards Aquifer is a karst aquifer system with several large springs that emerge from the aquifer. In a few of these springs, there are endangered species that live only in the spring runs, so there's a large interest in maintaining flow at those springs to support ecological flows. The Edwards Aquifer Authority has been tasked with managing this important resource, and as part of their management, they use a ModFlow model to evaluate possible management strategies to mitigate drought conditions. More recently, they've become interested in understanding how uncertainty may be affecting their ability to simulate and estimate the efficacy of those drought simulations. And so they partnered with the USGS recently to take that ModFlow model and evaluate uncertainty. So the primary focus of this work was again to evaluate the uncertainty and the important simulated outcomes under drought conditions. But the secondary focus for the nerdy scientists who were involved was to demonstrate how we can use these ensemble methods in really high dimensions, but in reproducible and transparent ways. And the way we did that was we constructed our PEST interface around this existing model in a programmatic way using Python and PyMU and FlowPy. As you might imagine, in a high-profile system that's highly managed like the Edwards Aquifer, there's a lot of historic observations. And in fact, some of those observations have been collected at the locations of management interest. giving us what we expect to be a blended subspace dependence. We use 330,000 parameters to represent known and expected model input uncertainty, including grid scale geostatistical parameterization, shown here at the bottom for a single realization. We also included parameters on boundary conditions to estimate, to account for uncertainty in groundwater extraction rates and recharge rates. What's important for decision making is the spring flow at Comal and San Marcos Springs and the water level at the two so-called index wells. These wells have been shown to track very closely with the spring flow, and in fact, water levels in these wells are used to implement drought triggers. Here we're going to focus mostly on Comal Springs. So here on top I'm showing the results of the PES-PPIS analysis for history matching, and on the bottom is the hindcast results for the drought of record. The red line, the red solid line, is the observed values. The black dashed line is the existing model, and the blue traces are the posterior realizations from iterative ensemble smoother. You can see on the top we're fitting historic conditions pretty well, but on the bottom, in the hindcast situation, there's still significant amounts of posterior parameter uncertainty, shown as the spread encompassed by the blue traces. Specifically, what we're interested in, though, is how many consecutive months did the flow at Comal Springs go below 30 CFS, and you can see in 1956 to 1957, the flow actually went to 0. So if we process those results up, now we can see the prior and posterior probability distribution of this forecast. In the prior stance, the gray histogram here, we can see that in fact we can't discount the possibility that there would be 36 to 40 months of consecutive flow below 30 CFS at Comal. But through history matching and through assimilating prediction relevant information into the parameters, we now can reject the possibility that there's going to be an extreme or prolonged period of consecutive no flow months, and instead we're centered more between the period of 0 and 10 consecutive months, and 6 months was actually what was observed in the historic period. If you're interested in checking out this work, we recently published this in the Frontiers in Earth Sciences, and we've also gone to great lengths to preserve our workflow through scripting. You can download the model files and the scripts used to implement this analysis, and actually the scripts used to make the figures that went into this publication at the GitHub repo listed here. I encourage you to check that out. For the final part of this video, we're going to now focus on something that's very simple to implement, but that is incredibly powerful, and that is prior-based Monte Carlo. Prior-based Monte Carlo is simply Monte Carlo that is implemented using only the expected parameter values and ranges defined by expert knowledge. That is, we're not trying to include any sort of information or data assimilation from observations. We're only using our expert knowledge and our expected parameter values to define the uncertainty in the parameters. This information is typically encapsulated in the pest control file through the mean, which would be the initial parameter value, and the plausible range, which would be the parameter bounds. So how would you do a prior Monte Carlo? Well, you set up your pest interface just like you would using these variety of methods. In this case, you want to use lots of parameters, since there's no computational penalty for using lots of parameters in a prior Monte Carlo. You want to set bounds to be meaningful in a physically plausible sense, and you want to set up observations in your pest control file for any of the things you might be interested in. Then with PES-PPIS, if you specify the inop max control variable to -1, it will generate the prior parameter distribution for you, draw the ensemble from that distribution, and run the ensemble forward in parallel for you. Then you simply enjoy the results. So what is the real value of prior Monte Carlo? Well, in the traditional modeling setting, as we're building up the model and adding packages and processes and complexity, we would simply run the model once and look at the results and say, yeah, I guess that's good enough. Here's one of those situations. The observed value is here in red, and the gray is the simulated for a surface water flow observation location. In this case, we would look at this, maybe scratch our chin and say, I think that's pretty good, but we think it's pretty good simply because we know there's uncertainty in the model inputs, which means there's uncertainty in these outputs, so we really don't have any context to judge how well the model is performing in this prior setting. But prior-based Monte Carlo, running the model just a few tens of times, can bring an incredible amount of context and diagnostic power to bear early in the modeling analysis. So here's our single run again. It's sort of meh, but now we run the model 50 times, and suddenly we have a much clearer picture on what the model is and isn't doing well. On the top, it looks like it's doing fine, but now in the context of these 50 realizations, we see it's doing fine at some times, not so well at other times. And in fact, the not so well at other times brings us to the topic of prior data conflict. Those of you who understand what happens with prior Monte Carlo will immediately recognize that there's a problem in this picture. Again, prior Monte Carlo representing maximum parameter uncertainty, here in the gray traces, and the observed data in red. Now, because we've used as many parameters as we can for prior Monte Carlo, and we've set these to have conservatively wide bounds, this prior Monte Carlo output, shown here in gray, represents maximum parameter uncertainty in the model outputs. That is, that's the maximum range of output possible at this location, using all the parameters we can justify and using physically plausible but conservatively wide bounds. And the fact that the model ensemble in gray doesn't cover the red values, as shown here, the gap on the very far right, that's a big problem, right? Do not continue with parameter estimation in this setting, because if you continue with parameter estimation in this setting, the only way the parameter estimation algorithm, no matter which one you're using, is going to force the model to go from the gray to the red is to use extreme parameter values. Extreme parameter values, another word for that would be biased. And biased parameter values is a guaranteed way to get yourself to a model failure. So what do you do about prior data conflict? Well, you can only detect it in this stochastic setting. That is, you have to run the model many times to actually build up a statistical picture of what is the output range the model can cover. PES-PPIS and PES-PPDA will warn you if it detects prior data conflict, but the process of resolving prior data conflict, well, this is where modelers really earn their money, because there's no clear-cut way to do this. It's going to involve diagnostics and digging into the model and the processes and the parameters that are being used and trying to understand why the model is deficient in certain ways. So wrapping up, ensemble-based methods are one way to do history matching and uncertainty analysis for environmental modeling decision support. It's one of many tools that may be needed. They're not without issues. We've covered some of these here, and also some techniques to deal with those issues. Current and soon to be released tools implement several of these algorithms. And if you don't believe in anything else, please, please, please start doing prior Monte Carlo as frequently as you can justify. So thanks for watching. I would like to acknowledge all the present and past contributors to both PES++ and PyMU. If you have any questions about the topics I covered today, please email me at the email address shown. Thanks.
Okay, hello again. Now you're back to me as we just finish off this webinar. I want to talk about something completely different, now for something completely different, and that is using modeling as a scientific instrument. This is a variation of posterior uncertainty analysis that I call direct predictive hypothesis testing. Now, there is a bit of a problem with the methods we've been talking about so far, and that is the problem of connected permeability. Whether we're using ensembles, whether we're using pseudo-linear methods, we're using parameter fields which, as I said earlier, have to be adjustable. Now, therefore they have to be a bit abstract, and therefore they may not be able to represent some important things in some contexts very well. For example, connected permeability, born of structural features such as a fault or an alluvial channel. They have to be represented in the prior field, and they have to be represented as those parameter fields are adjusted. And that's kind of a problem that the technology still hasn't got over yet. We may run the risk of underestimating uncertainty through adjustment of those parameter fields to conform with history matching constraints. How can we overcome that? Well, one way is to direct implementation of the scientific method. Now here, as groundwater modelers, we run the severe risk of actually becoming scientists. So, what's the scientific method? The scientific method is you propose a hypothesis, you see whether you can reject it. You can never accept, you can only reject. In a decision support context, what's that hypothesis? Well, as we spoke about last webinar, why are we building a model? To manage. Why are we manage? Because something's might go wrong. The hypothesis we want to reject is that something goes wrong. Okay, how can we test that hypothesis? Well, suppose we've just calibrated a model. Suppose we've just got a minimum error variance set of parameters that allows us to do the history matching. What if I now add one extra observation to my calibration data set? What if I actually observe that the worst happens? Well, if I can actually then recalibrate that model, and if I can still get a good fit between model outputs and field data, and if the parameter field that allows me to get that fit isn't geologically unreasonable, doesn't make a geologist vomit, then I can't reject a hypothesis that will happen. And if PEST needs to introduce connected permeability to make a bad thing happen, by God it will. And it's up to us to say, oh, that's too connected and the permeability is too high in order to reject a hypothesis. It throws responsibility back on us. It introduces subjectivity to the decision support modeling process, but it was always subjective because by now you realize there's so many decisions we have to make about appropriate simplification, appropriate parameter abstraction, and things like that. So just putting this on our schema, suppose we've calibrated a model, good fit with the data, minimum error variance parameter field, a sample from the prior. So now look at the center here, we observe that a bad thing will happen. We recalibrate. And if we find that, no, we're still fitting the historical data pretty well, this still can be construed as a sample from the prior parameter probability distribution. We have a sample from the posterior, which makes the bad thing happen. We can't reject that hypothesis. And what we may even do is say, well, if PEST has needed to introduce a bit of connected permeability here, that doesn't look too bad. I may even revise my concept of what constitutes a suitable prior here. And remember, we're working with abstract parameter fields, and it's a little bit hard to translate geological knowledge sometimes into those abstract parameter fields. Maybe we've learned something. Anyway, it'll be subjective, and it's our choice whether we say it won't happen or it will, and we're the experts. That's our job. But we have in front of us the information necessary to make that call. So the good things about direct hypothesis testing, well, you go straight to the heart of the problem. You go straight to the bad thing you don't want to happen. You don't mess around with prior parameter fields which may or may not be suitable for a particular context, because most geological media are a lot more complex than the more simplified parameter fields we normally use in adjusting these parameter fields to satisfy calibration constraints. The bad thing, well, it's numerically intensive. You've got a history match under past and future conditions. However, we may be able to we can reduce the numerical burden of this through using randomized, Jacobian and or ensemble methods, which are pretty much the same thing, in undertaking this direct predictive hypothesis testing. Other methods, well, some of you may have noticed I have not mentioned Markov chain Monte Carlo, even though it is the kind of method of choice for sampling the posterior in normal Bayesian workflow contexts. Normally, we don't use that in groundwater modeling because this doesn't work too well where parameter dimensions are extremely high. And I just mentioned here data space inversion. That's supported in the PEST suite. This allows you to quantify, get an approximation to the uncertainty of a prediction without having to actually estimate parameters. As a result, the model run burden can be very frugal. And you might need this if you've got a big, fat, horrible model that's numerically delicate and takes too long to run. So this is something, a kind of almost a method of last resort, which can still be effective even though we may have a model which we can't do these other things we've been talking about with. So, conclusions. So this then brings me to the conclusion, not just of this webinar, but of this webinar series. And what we've talked about is a number of different ways which we can directly or indirectly implement the scientific method. And so, since the beginning of webinar 1, we've kind of come full circle. In webinar 1, we stated that we need to redefine the concepts on which decision support modelling rests so that environmental decision making and debates associated therewith can have science and logic as their context. And I'm hoping that by implementing the scientific method in ways that we have described, that we as a profession can take groundwater modelling into a new and hopefully brighter age. We can turn a groundwater model into a scientific instrument which can depict those things which we can be known and can quantify the extent to which other things cannot be known. If it proves necessary, we as modellers should leave decision makers in no doubt that bad things can still happen if a certain course of management action is adopted. At the same time, we, as modellers, have the ability to bestow worth on existing or imaginary data by identifying those data which have the most potential to reduce the uncertainties of decision-critical predictions, now and into the future. But most of all, I hope that by following the principles and practices that I, Catherine and Jeremy have outlined in these last 4 webinars, that we as a profession can return integrity to a pursuit that has been sadly tarnished through an ever-readiness on the part of some modellers to serve the financial or political interests of those who pay them by weaponising models in courtroom and media battles under the pretense that, with the aid of a model, we can see into the future. We cannot see into the future. We cannot simulate what happens under the ground. We can only assimilate data and make information available to those who wish to base management of our precious environmental systems on facts connected by logic. That is, on the scientific method. And with that, we end this webinar and we end this webinar series.